So that's this design is equivalent to we have a direct velocity feedback like this. If you happen to have this design, but you are not always lucky like this. Okay, let us go back. Let us go to the discrete time model. Let's look at discrete time model. The same thing. The discrete time model, you have xk plus 1 equal to axk plus b, yk equal to cxk plus duk. Then a and b is just for this system. And if we have a control force u equal to fx, then f1, f2, wk, and w dot k, then that means the f1, that the wk plus f w dot k, and that x here. The x here is just like your homework there. The x is w and w dot k. All right. And the same thing, we'll talk about this later too. All right. Okay. Now the x there, the xk, here we have xk defined to be wk and w dot k. All right. So if we have u equal to fx, now that means f1 wk, f2 w dot k, then our closed loop system will become like this on the top, on the bottom of the page 9 in here. And that's the closed loop design. However, that I am missing some plus or minus there. I think your notes is okay. But just this computer is not compatible with my computer. That's what happened. Okay, let us look at example. The spatial case. Delta t equal to pi over 2. Your homework is delta t is not pi over 2. It's different. Okay. Now the closed loop system will become a plus bf equal to f1, f2 plus 1, f1 minus 1, f2. Then open loop eigenvalues is the open loop, closed loop eigenvalue will be a plus bf minus lambda I. That's the determinant equal to 0. That means we have lambda square minus f1 plus f2 lambda and so on. All right. Now, our open loop, what is our open loop? Now, our open loop for this case is, okay, now. What is our open loop? All right, this open loop. The open loop is lambda square plus 1 equal to 0. And that's our open loop for this, for this discrete time. And we know that that's 1. That lambda equal to plus minus I2. But in this discrete time model, you have to be very careful on this because a discrete time model is image circle here. Okay. My cross loop. My cross loop pole. I want my cross loop pole equal to lambda equal to half plus minus half I, right? And that is, if you again in the inner circle here, it's not, and then I have half and half I. That means here. That's my cross loop pole. And That's my closed loop pole. And if you notice that this lambda, this is not negative. So in the inside of unit circle, as long as you are inside the unit circle, this is stable. As long as outside the unit circle, this is unstable. Agree? Okay. That is, this is my open loop. This is my open loop. And this open loop is on the unit circle. It's on the unit circle means as long as it's on the unit circle, on the unit circle, on the unit circle, that means no damping. All right. So I want to move my open loop pole from here to there, and that from here to there. Then what kind of U I'm going to get? The U. So U is F1, the WK plus F2 W dot K. That's my U, K. Now if I do this, if I do that like the trick back here, because my closed loop eigenvalue problem is this, if I just give you F1 and F2. Now if I give you the closed loop eigenvalues, then that's my, the eigenvalue problem becomes lambda square plus lambda plus half equal to 0. Now if you do this, then we know that F1 plus F2 equal to minus 1 from there. So from there, you compare these two equations. You compare the equation here, lambda square minus parenthesis F1 plus F2 parenthesis lambda plus parenthesis 1 minus F2, F1 plus F2 parenthesis equal to 0, and lambda square plus lambda plus half equal to 0. You compare these two equations. If you compare these two equations, then you will find out F1 plus F2 equal to minus 1. And here, the 1 minus F1 plus F2 equal to half. Now from these two equations, then you will be able to solve F1 equal to minus 1 over 4, F2 equal to minus 3 over 4. That's the solution. So, now, if F1 my F1 is minus 1 over 4 WK, and my F2 is minus 3/4 W dot F, the parenthesis K, if I have this feedback, then my open loop pole will move from the here to there, here to there. That means my original system has no damping. After I move here, now we have a damping. See, that's damping because it's inside the circle. Now, the damping, if you look at the length of here, that means the eigenvalue. If I look at the length lambda length equal to square root 1/2 square plus 1/2 square. That's the length. Then that means square root the 1/2. Right. So the length is square root half. That means this is the length. As long as this length less than 1, then the system is supposed to be asymptotically stable. because that's inside the unit circle. So if you look at the length of your discrete time system eigenvalues, if you look at the length of discrete time system eigenvalue, you will know if the system is stable or not, is asymptotically stable or not. Understand now? So, for this system, if we give them feedback like this, then my open loop system become my closed loop system. And because my open loop system become my closed loop system means I have no damping system. The no damping system become with the damping system. As a matter of fact, this is really far away from this unit circle here. That means this is really stable system. Because that's the only square root half. And that's this event. We consider this is a very stable system. Okay, let's take the 10 minutes break.